Thanks. I'm delighted to join you. I want to pull together themes from the last 2 days, broadly around the notion that the future is here today. It's just not uniformly distributed. So we appear to be living through an AI revolution, but depending on how you count, this is actually about the 5th boom-bust cycle. It's done that. But in fact, if you look at the numbers, and mouse to the bottom, thank you. If you look at the numbers, roughly a year ago, the number of ops per second in a large computer matched the number of ops per second in our brain. So all that's really happened is just scaling. That the number of ops per second, the amount of data, has matched the complexity of the brain, and if computers weren't doing something roughly on the order of the brain, we'd be derelict in our duty. It's just a scaling exercise. That's what's happened. But here's the part that I'm more interested in. If you look at the chip fab making the supercomputer, it can place about 10 to the 17 parts per month. While you're sitting there digesting your breakfast, you're right now making about 100 supercomputers a second. You're placing 10 to the 18 parts per second. There's orders of magnitude difference in this fabricational complexity, in breaching this boundary between the digital and the physical world. We're orders of magnitude away from that. So to help close that gap, I founded with some colleagues the Center for Bits and Atoms. We've done things like we did the first faster than classical quantum computations. We implemented first searching and then factoring using spin nuclear magnetic resonance. We showed how to do cryptography in materials, fluidics, to use universal digital logic. We were part of inventing the Internet of Things. That's the kind of research we've done. Breaching the boundary of digital and physical. Given that background, I feel qualified to observe that computer science was one of the worst things ever to happen to either computers or to science. And I mean that very seriously. It's a mistake. I worked once removed with the founders. I worked with the students of Turing and von Neumann. And the whole edifice of computing is based on the fiction that computing happens in a world that isn't physical. And given that background, once you recognize computing is physical, one of my students, Jason, built and runs all the computers at Twitter. And my student, Rafi, built and runs all the, Jason runs all the computers at Facebook. My student, Rafi, built and runs all the computers at Twitter. And the reason they can do that is because I taught them not to believe into computer science. They have to take billions of dollars, tons of mass, and megawatts of power and make information, and you can't believe in digital. It's a fundamentally physical exercise to breach that boundary. So coming out of the work of these remarkable people really is this roadmap. We have one Earth, about 1,000 cities, 1 million towns, 1 billion people, and about 1 trillion things on Earth. If you look at the history of computing, across the river near the tours this afternoon, that's the Whirlwind. It was the first real-time computer at MIT. It filled 2 floors of a building. There was one of those. It got transistorized and spun off the mini-computers, and there were thousands of those. That's Kernighan and Ritchie inventing Unix. That begat the hobbyist computers, then the personal computers, now Internet of Things. So computing went from 1 to 1,000 to 1 million to 1 billion to 1 trillion. Not as a metaphor, just numerically. MIT invented computerized manufacturing in 1952, connecting the real-time computer to a milling machine. There was one of those, and my lab has the successors to that. We're developing fab labs that are like the mini-computers of fabrication. We're developing machines making machines that are like the hobbyist computers. We're developing assemblers that are like the personal computers. And finally, self-assemblers that are like the Internet of Things, with a roadmap to scale from 1 to 1,000 to 1 million to 1 billion to 1 trillion. Now, what's important about that picture is that's not sequential in time. They're all here today, they all exist, but their impact ranges from now to decades in the future. So to start running through that, initially for outreach for the National Science Foundation, I set up a mini version of my lab at MIT. The lab at MIT, the goal was one of every machine to make anything. And so if you come on the tour, that's what you'll see this afternoon. But that's tens of millions of dollars. This fab lab was a mini version. It's about a $100,000 investment, 2 tons, fills a room. It has a 3D printer, but that's just a little corner of the lab. It has all the other machines you need to go from digital to physical and physical to digital. And with those, you can make everything I'm showing you. And then we had an accident, which was we were supposed to set up one as an outreach project and go back to work, but they went viral. And so on the bottom, I'm showing you the world map of where they've sped to. One of the interesting set of sites is we we helped Dassault SolidWorks set up one in Waltham. And that was so successful that we started these all around the world. So that's the team with Paul Kagame in Rwanda. We set up a lab working on import substitution. That's one in Bhutan with Bhutan's prime minister, where the country is based not on GDP but gross national happiness, but they buy crap trucked in with India. So this was a lab to embody gross national happiness. Earlier this year, the team, in fact, Abhishek, who's here somewhere, who runs the Waltham lab, Abhishek, there was with this. This is the southernmost city on Earth. This is the last stop before Antarctica, at the bottom of South America, in Puerto Williams. Beautiful natural resources, impossible supply chain. We're going to do the next one in the series with Dassault SolidWorks in the spring in Nepal for humanitarian relief. This wonderful network of labs in this collaboration. And here's the scaling. The first 5 points on the top are Moore's law, most important graph in history, doubling of transistors. Gordon Moore predicted it might go for a decade. He was wrong. It was 50 years. You heard about Moore's law earlier. It actually has ended. That starting about 2015, it turned over. So Moore's law, that really has ended. The bottom graph is Fab Labs. And so this is 10 years of the doubling of these Fab Labs. They've been growing exponentially. There's actually more data than Gordon Moore had. And so the only thing that's rational at this point is to believe that's going to go for the next 50 years through the scaling of 1,000, million, billion, trillion, meaning anybody can make anything anywhere, is what this points at. And so to start tracing that out, we had to create a thing called the Fab Academy to teach the skills. Bright kids would come to these labs, fall off an educational cliff. So as this runs, this was a student in the Fab Academy who, for his homework assignment, he wanted food. This was in a little lab outside Barcelona. He had no skills, so all he could do was make a sketch. Then he starts to learn CAD tools. Then he learns prototyping. Then he learns large format machining. Then he's learning instrumentation in work groups. So it's not an online class. You don't go to a class at a distance. It's a network. It's a distributed class. And we've done a class with George Church to teach biotechnology this way. We've done a program to teach textile technology. Around here, he's learning to design electronics, so this is his Arduino. Again, he had no technical skills coming in, and then he connects this whole system, and I love the picture coming up. This is his first lettuce. And this wasn't a startup, it wasn't a team. He learned how to do all of that once you have access to these tools. So if you think about that example, the most sensitive battles today are about things like tariffs, jobs, inequality. It's all a false dichotomy. It assumes you need a job to have work, to get money, to buy something. But if you can go from digital to physical, you can produce it. It's not utopia, it's not free, but most of what governments and to a great extent businesses do, you don't need if consumers can become creators. And so on the left is a lab we ran with the Obama White House. If you know the geometry, it's high-power lasers we brought right outside the window of the Oval Office. Security was scared. Obama loved it. On the right is Barcelona's mayor. Great design sense, over 50% youth unemployment. A whole generation can't work. He's starting a 40-year countdown to urban self-sufficiency. Instead of products going in and trash going out, they want the city to produce what it consumes. Below is a list of other cities signing up for that Fab City commitment, not just smart, but a Fab City, able to produce what it consumes. In the middle is really interesting legislation just submitted.
I'm United States Congressman Bill Foster, and I'm one of the few members of the United States House of Representatives who was a scientist before entering politics. So I often tell people that I represent about 1/3 of the strategic reserve of physicists in Congress. But when I came into work each day in physics, my first stop often wasn't to my office computer or some meeting, but to the laboratory machine shop to check on the progress of some parts that I designed for an experiment or for part of an accelerator. So I believe I can safely say that I'm the only member of the United States Congress that knows how to program numerically controlled machine tools. I'm proud to announce that I recently introduced legislation in the United States House of Representatives which supports the goals and mission of the National Fab Lab Network as in the best interests of our people and the best interests of promoting the goals of greater science and technical education, greater access to research and production tools, and empowerment of individuals to understand and use technology to improve their lives. You can think of the NFLN as a new kind of national lab in the United States that's a cloud laboratory, a national network of connected local labs. I've been lucky to have the chance to visit Neil and see.
So this really interesting bill charters in the national interest universal access to digital fabrication. In the same way that we expect access to computing and communication, it's in the national interest to have the means to make. So to meet those goals, we've done a lot of work on rapid prototyping machines. These are a bunch of companies we spun off, like Formlabs, a local one, is now a $1 billion unicorn, expanding access to high-performance fabrication tools. But in a sense, these are a disappointment because we don't want you to go to the lab to use the machine. We want you to go to the lab to make the machine. We want labs making labs. And so this is how we're making labs now. In fact, that's a 3 kilowatt fiber laser for metal cutting. The remarkable student who designed that is now working in my lab. And the way machines typically today are like BitNet. They have a lot of configuration in them. The way we make machines now is you have modular machine generators, and then that isn't what it looks like. It's not a machine controller. It's actually a node in a data flow network. It's a node in a distributed computation. And then you make a software data flow graph of the intelligence of the machine, and then you overlay that on the hardware of the machine. And it's very much like an internet architecture. So you can add and remove degrees of freedom, and you can close control loops without having to reconfigure the state of the machine. The machine becomes a distributed computation. And a really interesting spin-off from that we did with Dassault SolidWorks was Fab Connect. There's a lot of questions about what's the future file format to make things, and the answer is there isn't one. What there is computation. And so we worked closely with Google and Mozilla and broke browsers many times, building high-performance real-time computational geometry in a browser. And then this is a tool that lets you be in a 3D experience design environment, and instead of exporting a file, you can take that cloud and you can connect it to the machine cloud. So you can pump geometry right from that cloud through this cloud into the machine cloud without ever tossing files over the transom. And so in a really interesting way, taking the software environment and coexisting with the physical environment, building this hybrid. One of the things that's come out of that, picking up on the materials discussion, is there's a materials genome initiative in the US, a national initiative for advanced materials, but it's sort of stuck. Very few people have access to the means to develop, measure, and model materials. And so what we're doing in this project is rapid prototyping of advanced materials instrumentation, expanding access to the means to develop advanced materials, and then connecting that high-performance computing to model them so you can propagate back from these measurements into the materials development, in a sense democratizing material science. So this is a close collaboration with NIST and Argonne. Now, the Fab Labs can do everything I told you. The problem is the thing you can't read is the inventory. When we send a lab like we did to Port Williams in the southernmost city on Earth, you can make everything I showed you, but we have to send all of this stuff, resins and electronic components. The bottom is a blow-up of the digital components. And so you need all of these inputs to make almost anything. So the inspiration for me is your inventory is 20 parts. You're made out of 20 amino acids. And what's interesting is they're not interesting. They're hydrophobic or hydrophilic, basic or acidic. They have these simple properties, but by composing them, you make motors and sensors and processors and all of that by assembling them. You can design with them. This is work we did. We were part of the collaboration to make the minimal synthetic organism, where you design life in a computer and print it out. And this is a project we did to print molecular scale structures. And one of the offshoots from those research projects was, you may have heard of a CAD tool for molecular design called CAD Nano. All of that is digital design with molecular building blocks, but you're limited to those material properties. So biology doesn't have high electron mobility or refractory properties. There are a number of properties not available. So what's been really driving this research roadmap is there's a hierarchy in biology from a coding sequence to geometrical motifs, to functional elements like electron donors, to molecular machines, like what you smell with or what you think with. And in those, the code doesn't just describe something, the code actually becomes the thing. It's a fundamental distinction. There's no reason you can't do that in inorganic systems. And so we've been looking at how you build the hierarchy of primary, secondary, tertiary, quaternary structure with non-biological materials. And so here is a result. This is an interesting machine that's a cross between a 3D printer and a pick and place, and it's to build ultimately itself. The goal for this is to make an assembler that can assemble itself out of the parts that it's assembling, a self-reproducing system. Robots are made out of lots of custom parts. This one has a very small set of building blocks, a rigid part, a flexural part, a magnetic part, and it can assemble them into a three-dimensional volume. And with those, you can make micro-robots. And so a rigid part is a structure, a flexible part is a hinge, 2 of them is parallel transport, 4 of those is a 4-bar linkage, a 1-bit actuator moves a bit, 2 of those does cyclical motion, and these are along the way to making one of these machines that can make itself out of its own parts, a self-reproducing system. Then there's a hierarchy. The machine that makes itself out of its own parts can in turn make bigger robots, and so a few years back, we set the world record for the highest modulus ultralight material by linking loops of carbon fiber. We showed instead of having tooling the size of a jumbo jet to make a jumbo jet, you make little parts and link them in sparse volumes and make much higher performance structures. Recently we used it, you can't read the sign, but the lower left is NASA Langley's wind tunnel, and we made a morphing aerostructure that's about 25 feet, the size of the biggest wind tunnel, by linking little loops and including designing the deformations of the structure. And this is a thing that's just coming out now, which is to build these, there's a really interesting kind of hybrid material robot system. These robots don't navigate globally, they count steps locally. They're missing most of the control systems in a robot because every step error corrects and re-registers to the lattice, but they can work together to build in 1D and 2D and 3D and then collaborate in swarms. And so these hybrid material robot systems means we're working with a number of groups. We're working with Airbus to replace the global supply chains that almost killed them with local production. So the final assembly is the only assembly. We're doing the same thing with Toyota to take little building blocks and have hybrid material robot systems to assemble large high-performance structures. And these involve building entirely new workflows for how you design and model these systems. So if you look at the scaling of all of this, the bottom is the number of elements you place in a second. The top axis is the number of elements you can place. The red points are today's most advanced manufacturing. The green points are the frontiers today of additive manufacturing. And way off to the side, the blue points are is molecular biology. And so by this recursion of making assemblers that can assemble assemblers from the parts they're assembling, we're looking to close this gap between state-of-the-art manufacturing today and the orders of magnitude off from molecular biology. And fundamentally, this rests on digitizing not the designs, but the materials. Digital communication and digital computation happened in the 50s. And those were based on showing unreliable systems can operate reliably. And that's not ones and zeros, it's actually a scaling property. Errors go down exponentially with the size of the code. Life is based on that same insight, but what you're digitizing is the materials. And we're learning to expand that from organic to inorganic. And so finally, if you can do everything I'm describing, it means we'll be able to place billions of parts to design complex functional systems. And there's a problem, which is it'll break Dassault's tools. Once we get to this limit of billions of degrees of complexity, and the systems I'm describing have form and function, so you can't separate hard and software, just today's design tools break. And so a really interesting person is Jan van den Brund. At Boeing, he was in charge of optimization, math, geometry, all of those functions, and he decided those were so broken, he just gave up and went to DARPA to reinvent design from scratch. And so again, if you think about the scaling curve, if we're going to place parts at the speed you're placing them now, with the complexity you're placing them, how do we design them? And so building on all the work I've described, what we've been looking at is morphogenesis. So the breakthrough of the year in science, every year Science Magazine picks a breakthrough of the year. This was it last year. This is morphogenesis. So upper right is a day in the life of a zebrafish. So there's the egg, it's fertilized, there's one cell, then there's 2 cells, then there's 4 cells, then there's 8 cells, then they start symmetry breaking, and at the end of the day you have a zebrafish. Now, what's so interesting about this, the breakthrough last year was not that it's understood, but that it was possible to trace the position of every cell and the expression of every gene. So the data is there. And what's so interesting about morphogenesis is your genome doesn't store you in the sense that nothing in the genome says you have 5 fingers. The genome has a developmental program, and at the end of development, you get 5 fingers. And the developmental program doesn't store the number 5. It has notions like symmetry breaking and gradients and properties like that. So evolution isn't random. If you made random changes to the genome, almost everything you did would either be inconsequential or fatal, but it wouldn't be interesting. The heart of evolution is it searches over a very carefully curated space, which is a developmental program. So in almost all of engineering, you design the thing, but that doesn't work at this complexity. You have to search over a program that produces the thing so that search is interesting. And in doing that, that's exactly the heart of the insight of deep learning. In the progress in deep learning, the way we search hasn't changed. What changes is the representation, to be able to represent enormous complexity. So we set out to ask, can you build engineering that works on morphogenesis with that abstraction? And so to do that, we had to do a do-over of everything. We had to rewrite multi-physics modeling for complex systems of enormous complexity. Then we had to inject this layer of algorithmic abstraction. So you don't search over the thing, you search over an algorithm that leads to the thing. Then you needed to search over populations to produce it. And then one of the hardest things is you need to guide it towards what you want, because in systems like this, the AI systems cheat. They satisfy the letter, but not the spirit of what you wanted. And so just as a warm-up for initial work on this, we took the simple but surprisingly hard task of rediscovering gears. So what's running here is multi-physics modeling over algorithms with population searching that didn't know anything about gears. And the question is, one of those is driven there's a driven boundary condition, there's a free boundary condition, and can you discover gear design? And so this is the stages of an AI waking up, and it never saw a gear, there's nothing to train it on, it just has to interrogate the physics, and eventually it learns out how to nicely mesh gears. And so we're scaling that to complex 3D systems with many more kinds of physics. To do that, we had to rewrite the tools at each of those levels. And one of the interesting things is I'm showing progress in generations versus performance on the gear design task. The green one is the result of hundreds of years of human evolution. Gear design is a very mature design. And the red and blue, orange and blue ones are what comes out of representations for this morphogenesis design. And for the domain we studied, it was actually possible to design gears much better than hundreds of years of received wisdom of what makes a good gear, just already at that early stage. So I started out by complaining about computer science as being a mistake because it ignored physics. The wasn't in the pioneers of computing, it was in the people following them. Von Neumann never wrote about computer architecture, really. He wrote a terrible memo about an early hack for the EDVAC. It's not a beautiful thing, but what he wrote beautifully about was self-reproducing automata. The last thing he studied in life was a computation that communicates its own construction. Turing never intended to be a computer architect. He invented the Turing machine as a theoretical construct. As a result from that, the computers that are in front of you right now are wasting much of their time because the Turing machine has a fundamental mistake. The head is distinct from the tape, which means storage of information is considered a different resource from manipulating information, which is unphysical. Nature doesn't do that. It means the computers around you waste much of their power moving information from where it's stored to where it can interact, even though the storage has the same computational power. It was never meant to be an architecture. Turing understood that. The last thing he studied was morphogenesis. He studied how genes give rise to form. And so the pioneers of computing understood what was really interesting about computing wasn't in the cloud, it was how it gets embodied, how it gets physical. We've had a few decades where Moore's law could let us ignore that. We now have a chance to access it. So I showed that roadmap of 1,000 million, billion, trillion. So, and I mean that literally, 1 trillion fab labs fitting in your pocket. And that's as fanciful as Internet of Things. In that scaling graph, we're about in the middle. Right now, we're in the mini-computer era. To do everything I said, you still need a room full of equipment, but not a whole building full of equipment. And that's the moment historically when email, the internet, video games, word processing, all of those things emerge. The technology will keep scaling, but we're living with it today. This is bonus material I did for the movie The Martian, where the question they were asking is, how do you actually survive on Mars? And so I'm describing how to go to Mars without luggage. And by that, what I mean is you don't go to Mars and repeat the whole industrial revolution. You essentially create life in non-living materials. You develop these 20 or so material properties you can compose to create a whole technological civilization. And back on Earth, what this means for things like the Fab City initiative is replacing global supply chains with this much more profound sense of local viability, local self-sufficiency, really, again, doing an end run around what seem like the biggest battles of today. You don't fight over the tariffs, you run around them. So I talk about all of this in this book. Usually at this point, I would stop a talk and you would clap and say, that all sounds interesting. My younger brother, Alan, developed and ran the world's biggest video game studio at Activision. And so he's used to dealing with millions of people using platforms. My older brother, Joel, ran the National Labor Relations Organization, and he solves giant labor management relations issues. And I would talk about all of this, and while everybody else was clapping, they would groan. Because they would think I'm being completely naive about how the last digital revolution played out, meaning it scaled technologically, but we've spent decades dealing with barriers to access and spam and fake news and catching up to the implications of it. And so the point of this book, and really the challenge to you, is there's a very solid roadmap for the next 50 years of going from digital to physical. We can see the technology, we can see the impact. Anybody making anything changes almost everything. I thought the technology was hard. In many ways, that's been easy. We just march along with that. What's been hard is building the organizational capacity, because it breaks what we think of as a school, as a government, as a business. You have to really invent how all of those things work. And the point of this book and the point of the challenge to you is that's today. We're right at this moment, the equivalent of inventing the internet. Rather than waiting 50 years to get the social impact wrong, we have a chance to steer it right. Thank you.
Thank you, Neil.